All right, welcome to part two in our exploration into DeMoivre's theorem. And part one's video, what we did was we set up a lot of the ideas, kind of hit some of the individual skills, set the ideas that allow us to use DeMoivre's theorems, and a lot of times we're going to say for powers, DeMoivre's theorem for powers. What we're going to do now on our second video is we are going to find complex roots. Now, when we find our complex roots, we are still going to be using DeMoivre's theorem, but something more interesting is going to happen, and that's why we're going to explore it. So first problem is going to be somewhat of a review problem. If you remember from Algebra 2, we had equations which looked like this that said, hey, x squared equals 64. Let's go ahead and solve for x. Now, if this is the case in Algebra 2, what we did was we did bring this 64 to one side. Now, a lot of times people say, hey, let's raise it to the 1/6 power. Let's actually go ahead and kind of go through the bad math of this. If we take x to the 6 to the 1/6 power, then we say 64 to the 1/6 power. A lot of times people say, oh, 64 to the 1/6 is 2. There's only one answer. And then we say, okay, wait a second. We're asking for an even number of roots. So we're going to go ahead and say plus or minus. Okay, now we have two answers, and everybody, those are our two real answers. Fundamental theorem of algebra, just kind of like as you get into it, it says if we have a power 6, then we are going to end up with 6 solutions. Now, this plus or minus 2 only gives us 2 out of the 6 solutions. The big question is, where are the other 6? So to do the other 6, I am going to do some special factoring. Hopefully you guys recognize that that is the difference of squares. So we could factor this into the square root of the first plus the square root of the second times the square root of the first minus the square root of the second. And then we also have some special factoring that goes on here. This is our sum of cubes. And if you remember the SOAP idea, that we'll take the cube root of the first plus the cube root of the second times the first squared, opposite sign, the 2 multiplied, always positive, the second squared. And then, so that is this factorization. And then the x cubed minus 8, we're going to factor similarly. That's also the difference of cubes, not the sum of cubes, but that's the difference of cubes. Same sign, opposite sign, and then once again, always positive. So if this equals 0, what I'm going to do is I'm going to clean it up and say this is where our positive and our negative 2 come from. Let me go ahead and actually plot these. If you notice, I have worked with, or I modified this graph a little bit just so that we can see all of our solutions just a little bit cleaner. So now, how do we find these? Well, we'll use quadratic formula. X will equal negative b plus or minus the square root of b squared. So 4 minus 4ac. So 4 times 1 times 4 is 16 all over 2a. So cleaned up a little bit, that's 2 halves plus or minus. This is the square root of negative 12 over 2. So 2 halves is 1, and then plus or minus. The square root of negative 12 is 2i times the square root of 3. So this will be 2i squared root of 3 over 2, or just I squared root of 3. And then quadratic formula on this one as well. So this one will be negative 2 plus or minus the square root of b squared, which b squared is 4, minus 4ac. Once again, we'll get 4 minus 16 all over 2. And we've done enough of this math that hopefully you guys will see that this is 1 plus or minus, or negative 1 plus or minus I squared root of 3. So our other 4 solutions will come from there. So 1 plus I squared root of 3. Now, hopefully you'll take a look right here, and in the calculator I already have the square root of 3 here. That's about 1.73. So we will have 1 plus, and if you notice, that ends up being on a very nice spot on the graph. So that is our answer of, let me go ahead and write it out. This is 1 plus I squared root of 3, 1 minus I squared root of 3. We will have negative 1 plus I squared root of 3. And then we will have negative 1 minus I squared root of 3. So what I did was I just plotted that one. Let's go ahead and plot this second point, this negative 1 plus I squared root of 3, which ends up being right there. Our third point, let's continue around. So this would be our quadrant 3 answer, -1 minus I squared of 3, which would be right here. And then our quadrant 4 answer would be right there. Now, one of the very, very neat aspects about plotting polar numbers and really polar roots, when you plot polar roots, you end up with what is a regular, I'm going to say regular n-gon in the polar plane. So this isn't because we are taking 6 roots here in essence, we are going to be finding all 6 roots, which creates a perfect hexagon in the polar plane. And then we can use some geometry aspects on that if we want to go further with it. I'm going to go ahead, just leave it at that point because that's a lot more bigger exploration in the polar. But this helps us understand all of our roots end up being an equal distance away. And that equal distance away is going to be based off of a struggling with the word here. This is a perfect n-gon, regular. In this case, is a regular hexagon. Not sure why I struggle with that one. Maybe because I'm back into more of like the algebra mode. So one of the questions I'm going to ask, and this is going to be kind of like a preview to all of my students who are listening, because this is a regular hexagon, we know that all of these are going to be 60 degrees apart. So these are 60 degrees apart because that is 360 divided by 6. If we have a, well, actually, let's go ahead and write it out. Let me do it up here. You know that if we have x to the 4th equals 1, we'll have our 4 solutions, and most people realize that that would be 1 and -1 are our 2 real, and our 2 complex are I and -I. And if you notice, each of these are 90 degrees apart, and they form a perfect square in the polar, or in the complex system. So just as a little heads up, I am going to be asking how many degrees are going to be between each one of our complex points. Now, one last notation before I actually get into the rest of the math. The very first one that we tend to get, so I probably should not have used orange, but it's too late now. So this ends up being our principal root. And to find our principal roots, you will see as we go through our problems to figure out where our principal root comes from. But the way we're going to approach this is we're going to take our principal root, we are going to go the equal number of degrees away to get to the next root until we end up back where we started with. So what ends up happening is we have 1, 2, 3, 4, 5, 6. Let me go ahead and change colors on this one. Let's change it to blue. This will be our principal root for this problem as well. Again, we're going to get into that. And so we'll go 90 degrees with the same radius, 90 degrees with the same radius, 90 degrees with the same radius. And then that's how we're going to come up with all of our different points. That's going to be our very, very efficient method. Again, start with the principal, go however many degrees around. Now, where this comes up with is DeMoivre's theorem for complex roots. Now, the first aspect of that is going to be if we are going to be taking our complex number. So if we take our complex number, in this case R, if you remember, we had cis, which is our shorthand notation for cosine plus I sine. If we take this to the 1 over n power, then what ends up happening is we'll take our radius to the 1 over n power, and again, using DeMoivre's theorem, we'll get to 1 over n times theta. Now that is where we end up with that, that portion of it. And so this 0, this sub-0, actually represents our principal root. So our principal root is going to be found by saying, okay, let's just apply DeMoivre's theorem in its pure form. So this is our principal root right here. Now, to find all the other roots, this complex formula really represents everything that I showed you before. So because this is very, very hard to teach on a virtual level, that's why I want you to go back to the geometrical level and say, we are going to start with our principal roots, figure out how many degrees are in between, and then plot our other roots from there. Now that is actually what this says, which if we ignored this, I'm going to put it back here in just a moment. If we take that, that is our principal root. And then what we're going to do is we are going to multiply n minus 1 times, or up to n minus 1 times, to really get to the rest of these. Again, how do I really want you to see it? Let's take our principal root and then add however many degrees to get to the next root from there. So let's, little technical difficulties. Let's get back on here. Okay, let's go from here. So our goal is to find all cube roots of -1 plus I squared of 3. To find all cube roots, the very first thing I want to do is let's put this into our polar form, because to apply DeMoivre's theorem, it just is so much easier to do this in polar form. So our modulus, or our radius, is going to be the square root of -1 squared. So -1 squared plus the square root of 3 squared. So that's the square root of 1 plus 3, which is 2. And our theta is going to be the inverse tangent of y over x, and the y is the square root of 3, our x is -1. We do need to check what quadrant are we in. X is negative and y is positive. That is quadrant number 2. So the inverse tangent of negative square root of 3 in quadrant 2 is 2 pi over 3. So our z in polar form is going to be 2 cosine plus I sine of 2 pi over 3. And if we're going to find all of our cube roots, then what we're saying is, what are all of my z to the 1/3 powers? So this is 2 to the 1/3 cosine plus I sine of 2 pi over 3. Actually, let me show that a little bit better. All of that to the 1/3 power, which then our principal root, which I'm going to call z sub 0, is going to be 2 to the 1/3 cis of 2 pi over 9. So everybody, that is one kind of ugly number, but that's okay. A lot of times we will write this as the cube root of 2 cis 2 pi over 9. That doesn't matter which way we write it. Basically, read whatever directions are being asked of you so that you know how to answer it. So that's our principal roots. How many other roots are we supposed to have? Since we want cube roots, there should be total of 3 roots. To get our second root, we need to look at and say, what do we need to add to this angle to get to our second answer? So our next root is going to be 2 to the 1/3 cosine plus I sine of 2 pi over 9 plus some specific angle. Now, what is that specific angle? We will take 2 pi, or 360 degrees, divide it by the number of roots we have, and that tells us exactly. Not sure why I jumped that way. So this 2 pi comes from the full circle, and we divide it into 3 parts to come up with the next root. So we're going to add 2 pi over 3 to get to our next value. So that would be the cube root of 2. 2 pi over 3 plus 2 pi over 9. This would be 6 pi over 9. So that would be cis of 8 pi over 9. And then to get to our next root, we're going to take that same radius. We're going to take our 8 pi over 9, add another 2 pi over 3. Probably should have just kept that as 6 pi over 9, so that we get cube root of 2 cis 14 pi over 9. So our principal root was right here. Our next root, which is 120 degrees, if you notice that, and then another 120 degrees to get to that next one. Now, I do every once in a while have students say, oh, I'm going to just go ahead and go further. Now, please know that we're done with this problem. We found all 3 roots, but suppose you didn't remember that. This is 2 to the 1/3 cis. We take our 14 pi over 9, and we add another 2 pi over 3. We are going to get cube root of 2 cis 20 pi over 9. Now, hopefully you recognize that 20 pi over 9 is really the coterminal with, so this is coterminal with 2 pi over 9. And if you notice, that was the principal root we started with. So what ends up happening is 2 pi over 9 on a graph is roughly right. Actually, that's a little bit further. Technical difficulties. You would think I would know this by now. I've only been doing this for about a month. So 2 pi over 9 would be right about there. So if we add 120 degrees, we end up right about here. If we add another 120 degrees, we end up with right here. So plus 120, plus 120, plus 120, we get back to where we start with. All right, on to our next problem. Our goal is to find the square root of I. So I probably should have been more specific and said find all square roots of I. So all square roots of I, I actually really don't like that. That bothers me. So find all square roots of I. I'll have to change that for next year. So find all square roots of I. So to find all square roots of I, first thing we need to know is there should be 2 of them. Let's take I, and so I'm going to write z equals I, or 0 plus 1I if we want to be more specific. Now to get that into our polar form, the radius, and this is where I like to draw it out, I is right here. The radius ends up being 1 because that's 1 distance away from the from 0. And then the angle that we have, we know I is straight up, so that would be pi over 2. So 1 cis pi over 2. And now if I want to take all the square roots, so z to the 1/2, to get my principal, this will be 1 cis of pi over 2 to the 1/2 power. So our principal root is 1 to the 1/2 cis of 1/2 times pi over 2, or 1 cis pi over 4. Now that is a known angle for us, so we could write this as the radius is 1. So the cosine of pi over 4 is square root of 2 over 2, plus I sine of pi over 4, and the sine of pi over 4 is also the square root of 2 over 2. So we end up with our principal root of square root of 2 over 2 plus square root of 2 over 2I. Now to get to our next root, and this should be our last one, we are going to take our full circle, our 2 pi, and cut it into 2 equal parts, which is just pi. So that pi is what I have to add to my angle. So our second root is 1 cis of pi over 2 plus pi, or 1 cis of 3 pi over 2. And I have a few distractions going on here, so my apologies. This actually should have been pi over 4. So when I add pi, that ends up giving me 5 pi over 4. So we have negative square root of 2 over 2, because that is the cosine of 5 pi over 4. And it's not plus, it's minus I sine of 5 pi over 4. Now what you'll notice is we should have some symmetry going on between these 2 points, specifically because we have 1 over here, and if we add it over here, we're going to get to, or we add pi, we end up with our quadrant 3 answer. So again, my goal is to tie as much of this together on a graphical level, as well as a numerical level, as well as an algebraic level. This right here is our algebraic step that we need to take. Now, to figure out how to get all the other points, it's easier to go more geometric and say we are going to add pi. And the reason why we add pi is because we take the full circle and cut it into the number of roots that we want. So, and again, both of these are our 2 answers. And we can just, this is my very, very quick graphical check on that. All right, so the rest of these is, the rest of this is all about, can we just apply it and apply it, yeah, in many ways as we can. So, or in many ways as we need to. So a lot of the times you will see this written as find all roots of -1. So what's written here is more of the algebra that we saw in Algebra 2. This is going to be how we're going to phrase that on the pre-calc level, but they both actually mean the same thing. So it's not just all roots, it's all 4th roots. So since it's all 4th roots, let's get into it. How do we write? So really our problem is like -1 to the 1/4 power, but this is going to be all of them. How do we write -1 as a complex number? that would be -1 plus 0i. How do we write that in polar form? -1 plus 0i, this is where I'd like to graph it to say -1 plus 0i is right here. The angle that we take to get there is pi. So this should be a radius of 1 cis of pi. And if I take that 1 cis pi, and I take that to the 1/4 power, and remember this is going to give us our, excuse me, our principal root. So our principal root is going to be 1 to the 1/4 cis of pi, 1/4 times pi. Let me write it that way just to be consistent. 1/4 times pi. So this gives me 1 cis of pi over 4. And we know pi over 4 is an angle, so the cosine of pi over 4 is square root of 2 over 2, plus I sine of pi over 4 is also square root of 2 over 2. So that'll be our first one. Now we want all 4th roots of this. So all 4th roots of this means we are going to then take pi over 4, or sorry, take 2 pi. Let me do this in a different color. So full circle is 2 pi, cut into 4 equal parts is pi over 2. So to get to all of the other angles, we have to add pi over 2. Probably should have gone to a different color right from the beginning. So our next one is going to be 1 cis pi over 4 plus pi over 2. Our next one is going to be 1 cis. By the way, that is 3 pi over 4. So 1 cis 3 pi over 4, which is negative square root of 2 over 2 plus I times the square root of 2 over 2. Our next answer, 3 pi over 4 plus pi over 2, which would be 5 pi over 4. And because I'm running into myself here, scoot that down. So that will give us negative square root of 2 over 2 minus I times the square root of 2 over 2. And then what should be our last root is 1 cis. Again, let's add another pi over 2. Show it here. Let's add another pi over 2. And we get 7 pi over 4, which now we are in quadrant 4. So the cosine minus I, this is actually a positive, minus I square root of 2 over 2. So all 4 of our roots, this is our principal root, and then our other roots. All right, so let's find all 4th roots of negative I. To find all 4th roots of negative I, again, like before, I'm going to put this into a form that I'm a little bit more familiar with. So it's in the complex number. Now the radius of this one will also be 1, because if we look on a graph, negative I is down here. The angle it takes to get there is going to be 3 pi over 2. So this is 1 cis 3 pi over 2. As 1 cis 3 pi over 2, we now need to take this 1 cis 3 pi over 2 and say this is my complex number. To solve, I want all 4th roots of negative I, so at least all of them. So what is 1 cis of 3 pi over 2 to the 1/4 power? Our principal root is going to be 1 to the 1/4 cis 3 pi over 2 times, I'm going to go ahead and move that over, again, more for consistency than anything else. Whoa. How about I just rewrite that? 1/4 times 3 pi over 2. So that would be 1 cis of 3 pi over 8. Now that's not one of our common angles, so I'm going to leave it that way. To get to our next root, just like before, we are going to add that pi over 2. So adding pi over 2 is like adding 4 pi over 8. So our next root is 1 cis 3 pi over 8 plus 4 pi over 8. 1 cis 7 pi over 8. To get to our next root, once again, we're going to add 4 pi over 8 or pi over 2. We'll get 1 cis of 11 pi over 8. And again, that step is adding pi over 2. And then if we add pi over 2 again, our last root is going to be 1 cis 15 pi over 8. And there are all 4 roots of negative I. And then on to a little bit more challenging of a problem. X cubed equals negative 8 minus 8i. So again, the translation of this one would be all cube roots of negative 8 minus 8i. This one's not going to be nearly as pretty. Let me go ahead and do this as a different color. Let's go to the green, or the teal color. So first things first, our radius is going to be square root of negative 8 squared plus negative 8 squared. So that would be the square root of 64 plus 64, which is the square root of 128, or that is the square root of 64 times square root of 2, or 8 square root of 2. So our radius is 8 square root of 2. Now to find the angle, I do like to do this as much on a graphical approach to it. Negative 8 minus 8i is down here. This should show you that, and I know this because that's my pi over 4 line, but in quadrant 3 is 5 pi over 4. So x cubed, sorry, this will give us our angle 5 pi over 4. Now, how do we officially show that? The inverse tangent, or theta, is going to be our inverse tangent of y over x, but in quadrant 3, which once again says our theta ends up being 5 pi over 4. Graphically is so much more efficiently on this, but sometimes we just need to go back to what we learned at the beginning of trigonometry. So our principal root is going to be 8 square root of 2 cis of 5 pi over 4, and we want all cube roots, so this to the 1/3 power. So this gives me 8 square root of 2. To be honest, I think I might actually just want to keep it as the square root of 128. And the reason why is because the square root of 128, this is 128 to the 1/2 power to the 1/3 power. So this is 128 to the 1/6 power. And then cis of 1/3 times 5 pi over 4. So multiplying those together, we will get 5 pi over 12. Not a known angle, so I can leave it in this form. And honestly, what is the 6th root of 128? 6th root of 128 does not have an even number, so we can leave it that way. There are going to be some problems that I'll be assigning that are going to be similar to this. So how would you do this in the calculator? Let's take 128 to the 1/6 power. So parentheses 1 divided by 6, and we will get this, we need that as a decimal. So put it as a decimal, 2.24 if we round. So 2.24 says 5 pi over 12. Please make sure you pay attention to the directions of how it's being asked. So to get our next root though, to finish this off, this will be 128 to the 1/6 cis, and what angle do we need to add? We'll take 2 pi divided into how many roots? 3. So 2 pi over 3. So what is 5 pi over 12 plus 2 pi over 3? So that's 8 pi over 12. So 128 cis 13 pi over 12. And last but not least, let's add another 2 pi over 3. And we will get 128 to the 1/6. This is our third root, or z sub 2, cis. If we add another 8 pi over 12, we will get 21 pi over 12. So all 3 of our roots are listed there. So hopefully you enjoyed this exploration into how this all works, and we'll remember, I've got your back and you've got your back. Have a good one.